Hi, this is my first video on section 7.1, and in this video I want to convince you that we're going to get probability from a probability distribution graph by finding the area. So let's talk about really quick what I mean by that. So let's start with, we did this example back in chapter 3 where we talked about the heights of U.S. women, and what we've determined back then was that the mean of all the heights, this was rounded I have to admit, was 64 inches. The standard deviation of all of those heights was 4.2 inches, and that they were normally distributed. What does that mean? What that means is we were looking at frequency distributions, but now we're looking at probability distributions, that if we look at that distribution, we will discover that it is shaped like a bell curve. Now, normal distributions are symmetric, so the mean is going to be right there in the middle. And if I go up one standard deviation, I will find that I'm at 68.2. And if I go up one more standard deviation, then I will find that I'm at 72.5. I'm going to use those markers to help me find the probability that somebody is equal to, well, do I mean exactly equal to? Probably not, but we'll, hang on, talk about that in a second. What I do mean is the probability that someone, a woman, in the United States is 70.5 inches tall. And that's not going to be exactly equal to, that's going to be approximately equal to, because here's 70.5, and do I mean that, or would I allow this woman to be maybe a couple of millimeters shorter or a couple of millimeters taller? I would, and I would still call that, I don't know what this cursor is doing, I would still call that 70.5 inches tall. So there's this little window around this. I'm going to exaggerate it and make the window just a little bit bigger than just a couple of millimeters. And so normally we read graphs by reading the height, but the height's not going to help me here because the height is changing. It's a little higher to the left and a little lower to the right. But what is fixed is the area. And so what we can do is we can measure the area, and this is going to equal the area under the curve. So the first thing we're going to do is look at uniform distributions because they're rectangular. And why is that helpful? Well, let me show you. So the last time we talked about uniform probability distributions was back when we were talking about the shape of a graph. And we talked about these distributions where all of the frequencies had equal height to each other. Now this first example here is going to be x1, which is going to be equal to, let's say we record the roll on a 6-sided die. It'll be a fair die. So I could get a 1, a 2, a 3, a 4, a 5, or a 6. These should be of equal width, but I'm doing it quickly. Now you might be noticing that the height is uniform. What I'm noticing is that the area for each of these values is equal to each other. And the probability of rolling a 1 on a fair die is exactly the same as rolling a 6 on a fair die. Now the first thing I want you to know about a probability distribution, about the graph, is that total area equals 1. So if I multiplied the width of this thing by the height of this thing, I had better get 1. Now why do we know this? You actually have all the facts to figure this out. You want to think about it for a second? So let's start with probability on a graph is the area. And total probability, which we know equals 1, is going to logically equal total area. So that's why that area adds up to 1. So this width here is equal to 6. There are 6 bars, each one with a width of 1. And so the height here has got to be, if you're ready for this, 1/6. Why is that true? Well, the width times the height is going to equal the area because it's a rectangle. See, that's why we're doing uniform distributions. And the area equals 1. And if the width equals 6, and if I multiply that by the height and get 1, well, now it's algebra just to figure out what the height is. I'll divide both sides by 6. So the height is 1/6. Okie dokie. So let me clear the screen here a little bit, and let's do a little bit of probability with this example. I cheated a little bit, and I got a nice clean copy of the graph now. Okie dokie, so let's find, oh heck, the probability that x is greater than or equal to 5. Well, that is going to be, I'm going to shade in when x is equal to 5. And I actually wanted to say this is going to be x1 because I'm going to have a second probability distribution in a second here. So, but I also want greater than 5, so I'm going to shade in the next bar next to it. Now there's two ways of looking at this. Here's the height of the graph. Oh boy. The height of the graph is 1/6, so you can say I have shaded in 2 bars, and so my area is the width times the height. It is 2 times 1/6. In other words, it's 2/6. But it might be easier to just say, well, I've shaded in 2/6 of the graph. In either case, it is also equal to 1/3. Now, the probability that x is strictly greater than 5, I'm sorry, I really meant strictly greater than 5. Well, now I'm not shading in 5, I'm only shading in the 6, because now the 5 is not included. Boy, I'm making a mess out of this. I'm going to have to do a clean graph again in a second. So now what's shaded in is equal to only 1/6 of the graph, or the width is 1 and the height is 1/6, so that gives us 1/6. So how's about what's the probability that x is exactly equal to 5? Yeah, I'm going to clean out the graph to figure this one out. Give me a second. So, oh, hang on. Sorry about that. I forgot to put in the nice clean graph there that I was promising you. So now we're talking about what's the probability that x is equal to 5. So to find probability, I shade in the area over the x value that we're talking about, where x1 is equal to 5, I meant to say. And I have shaded in 1 out of the 6 bars. Go ahead and think of that as 1/6. Or think of it as the width is 1, the height is 1/6, multiply those together and you'll get the area. Now, all of this is an example of a discrete probability distribution. It's not possible to roll a 2.5. I can only have a 1, 2, 3, 4, or 5, or 6. Let's compare this to a continuous probability distribution because I think it will surprise you. So this is my example of a continuous probability distribution. Up here I've got x2, and x2 is a continuous random variable. We're talking about the arrival times of a bus. Let's suppose a bus is supposed to arrive at 8 a.m., but if it arrived early or late, nobody would be particularly surprised. Let's say it could arrive 3 minutes early, or it could arrive 3 minutes late, or any time in between, and let's say it's equally probable that he could arrive at any time in between 7:57 and 8:03. Okay, so let's have a look at some probabilities here. The probability that x2, my second random variable, is greater than or equal to 801. Well, that is, we're shading in the area that's greater than 801. We're also shading in the area that's equal to 801, which is this line here. But I don't mean to be shading in to the left of the line. I'm just being sloppy there. It's everything from the line and to the right of it. Now what I've managed to shade in is 2 out of the 6 bars. So let's have another one here. What about I look for the probability of the arrival time being later than 801. So I'm shading in all of these values. I'm not shading in the line. Check this out. The probability of arriving later than 801 is also 2/6. And some of you are going to be saying, well, hang on, what about if we arrive at exactly 801? That's just a little bit more probable, right? Let's look at that. What's the probability that my second random variable is exactly equal to 801? And I don't mean a nanosecond earlier or a nanosecond later. To arrive exactly on the dot and not just a little bit off is, well, if we're talking area, that line has no width. So 0 times whatever the height is, oh, and by the way, the height is 1/6, is 0. Of course, we know it is technically possible to arrive at exactly 801, no matter how improbable it is. So we could say that it is 0 plus, but I just want to stress here, it is virtually 0. It is smaller than your calculator's capacity to compute. And so that's the part that will surprise people, and some people will get a little bit stubborn about, I have to admit. I'm going to reemphasize this in my next example, but what I want you to do right now is I want you to pause the video, and I want you to do example 2 on page 357. Have a look at that, and then come back to me and we'll do an example together. Okay, here's our last example. So, job number 1, draw the graph of the density curve. So, what does this guy look like? Well, there's a clue for you up in the description. We're talking about the reaction time of a certain chemical process. So this chemical process can take anywhere from 5 minutes on up to 10 minutes, no less than 5, no more than 10. And we know that the distribution of all of this is uniform. What does uniform look like? You need to know what uniform looks like, and it looks like a rectangle. If it didn't look like a rectangle, we wouldn't be talking about this. So the lowest value is 5 and the highest value is 10. Let's mark off some values in between. Trying to draw straight lines here. 6, 7, 8, and 9. Now notice my values are labeled on the line. That is because this is continuous. We are measuring time. Okie dokie. The width here is 5. The distance from 5 and 10 is 5. So that means the height is 1/5. On your worksheet that is going to be due in a week's time, I'm going to require that you label the height. I'm also going to require that you label the x-axis. So let's do that. That's the reaction time of the chemical. And you also need units. So that'll be in minutes. So that's part A. Let's do part B. Part B, the probability of the reaction time is between 6 and 8. So let's fill that in there. And so the question is, how much have I filled in? I have filled in 2 out of the 5 bars. It really is that easy. Okie dokie, let me clean the screen, and then we'll do parts C and D. So sorry, I've just realized I'm running out of time, so I want to stress 2 things here. In part C, are we being asked to find the probability that x is strictly between 5 and 8, or are we asked to find the probability that x is less than or equal to 5 and 8? And the point is, in the English language, it doesn't specify, and in math, usually it matters. Here, it does not matter. And so it's going to be from 5 to 8, sorry I've overshot, but I'm out of time, equals 3/5